Hello, what's up everyone? Today I'm gonna teach you how to do this problem from scratch. Like if you don't know how to use calculus in physics at all, you understand it from here. So yeah, this is a good start. And by the way, this problem is from the last day of ISA physics pre-course, and yeah, this has some calculus element in it, which I think a lot of people might be confused because they don't know how to use calculus in physics before. So I'm gonna teach just that. So first of all, let's understand the problem first. We have a rod or a stick or whatever you call it, which has like a length L and begin at x equals 0. This x thing is really important because it might come in handy later. Like a lot of stuff from now on will be a function depending on x or y or stuff like that. So it's really important for you to know where it starts and how much is each point is or where it is or stuff like that. So yeah, this is x-axis and it's in the horizontal line like this. And the rod start when x equal to 0 and its end when x equal to L. Yeah, straightforward, right? But the thing is though, the problem suggests that this rod has a mass density function lambda equal to this thing, kilogram per meter. Find xcm. What does this mass density function even mean? Some might ask. It's simple. Do you remember density? What the density is? It's like rho's equal to m divided by v. Or some might use d in chemistry or something like that, but it's just the density. From high school, you remember d is equal to mass divided by volume. This is the density, yeah. But the thing is though, in order for this density to work, you have to be in like a three-dimensional because your volume have to consist of something like a width, a height, and stuff like that to have a proper volume. But this rod is in one-dimensional, which have only x. There's no y or no z component here. So this is not the best density that you want to use to describe this rod. And also you can look at this unit here. It's kilogram per meter, which is one-dimensional because it's just meter. Instead, if you use like this volume here, you must divide something like a length by width by height, and you got the unit of like meters to the third power or thing like that. But this is just the one power. So yeah, this is not volumetric density. But what is this density then? So yeah, I gotta tell you first that density, there are three types of density. That is, it's depending on how much dimension object have, like the 1D, 2D, and 3D. 1D is like a rod, like in the example. 2D is like a paper, things that have surface area but really thin and stuff like that. And 3D is like a glasses or ice cube or something like that, which have like a depth and stuff. And we have different symbol for each of those, which we call, this one we call lambda, and this we call sigma, and this we call rho. But yeah, it's just name, but it's like a conversion that everybody use. So you might as well remember this because the teacher used this also. So if you know this stuff already, you can just tell that this was a linear density. But what does linear density mean? It's mean that this part of the rod have a different density than this part of the rod. Like this might made from styrofoam and this one might made from a metal or something like that. Or maybe it's the same material, it's just denser. But it's not important as of for now. But the key is though, this density is a function that depend on x. You can look at this thing right here. I will write it in another page because this look messy enough. We have lambda is equal to 1 plus this or not, or yeah, it's that kilogram per meter. It's important to write the correct unit so you know what it is. And then we find the xcm. Yeah, this is basically the whole problem here, isn't it? Yep. Okay, now we're gonna look at this picture from now. Okay, now let's go to see how we use this information to, solve this problem. The lambda here, if you remember, is the density, so but it's the linear density, so instead of the mass divided by volume, is be just mass divided by length. And yeah, you can write here like mass divided by length, and this is gonna be the surface area, and this is gonna be volume. Yeah, so the unit's gonna be different. This is gonna be kg per meter, this is gonna be meter square, this is gonna be meter cube. Yeah, like that. So yeah, we already know what this is. This is just used for telling how much dense in the specific part of the object. Like if you want to know how this object density is at the starting point, you just substitute x equals 0 into that, and you got the density here is equal to 1. Just simple as that. And if you here you got substitute x as an L, and you got 1 plus 1, which is equal to 2. So yeah, you can see here that the density here in each specific part of this rod is not the same. So if you want to find out how much mass is in each part of the rod, you must work backward. Like this is the definition of lambda, right? Is m divided by L. But if you want the m, which is stand for mass, you gotta throw this up there and got something like this lambda L. But you may have a question that this lambda here and here are different number. How can we multiply that thing by an L and got the whole mass? Nah, you can't do that. That's why you need to use calculus in physics, which is really important, by the way, and you use like a lot in the upcoming lesson. Yeah, like one day you'll find this as a conductor, and there are a lot of electric charge on there, and you have to find the electric field vector on here or some ways and stuff like that. Or maybe you find there's a current here and you need to find the magnetic field around it, and yeah, all of that you need to use calculus, which is really important and you must learn here. So yeah, let's tackle this together. And yeah, you might wonder, why do I need to find the whole mass of this rod? Because it is important that you need to use to find the XCM, which I will talk later, but now the goal is just find the whole mass. Okay, I know you might be confused why we do that. Let's talk about that now. I changed my mind. Let's talk about this first, and then we'll come back to find the whole mass. Okay, first, how do you find the XCM? The XCM, if you remember in high school, we have something like this, which is like two objects, and you need to find the CM, which will belong somewhere in the middle of it, like this, and when you do that, you use the mass of the object multiplied by the displacement that object is on, and then you divide it by the whole things, like this. If this have m1 and at the position x1, like I said before, you must have your position clearly, and x1 is like from here to here, you call x1, stuff like that, and from here to here you call x2, and this mass I have like m2 mass, stuff like that. If you want to find the center of mass in this object, you need to like do this formula, m1 x1 plus m2 x2, and divided by the whole mass, which is m1 plus m2, and then boom, you got xcm. Yeah, which is gonna be something like this arrow. You got the length of this arrow if you use this formula. But now there is not like the two separate objects which we can use. There are one whole long ass object here, which the mass of each part is also not consistency equally with each other. Like this part, specific part, the density is relatively low, so the mass will be something like really low, like maybe is equal to 1. And yeah, this part m is might be 2.5 or something like that, which is like somewhat higher. So you can't just use this formula anymore. You have to like, what you need to do, this is the whole concept of calculus, you take note. You must, chop this thing up into like a really small pieces. The piece so small that you can, find the density of this whole section as like a one number, because like if your pieces are too large, like you select the whole thing as a piece, this lambda here is 1 and this here is 2, so you can't multiply that together with the length, to get the masses. If you want to get the mass, you have to like chop this piece in like really small manner. So yeah, if I chop my piece small already, I might say that this whole piece have a lambda of like 1.2 or something like that, and you multiply that thing by this length, which is like a really small length that you already chop. It's maybe like 0.1 or something like that, and you get like this thing, this thing of this small section, and you need to add this together with all the other section. But you might say that, oh, this is hell, I gotta add like a millionth time. But no, that's not the case. You can just use the calculus to help you with that. I'll tell you how. But first we gotta plot the graph first. This is the graph of, the x-axis, but the y is not a typical y that you used to. I'll call this y as a lambda, and yeah, lambda is equal to 1 plus x squared by L squared kilogram per meter. So yeah, it's probably is something like this, with the n at the x equal to L equal to 2 and this place is equal to 1. This is the density function of this rod. You can see that toward the end of the rod, the density is higher, which means that the mass in this part is gonna be higher than this part also, if you chop it into like the smaller pieces. But let's look back at what we did before. We did chop it into the smaller piece like this. So if it's in this graph, it will be something like that. It's a smaller piece, and the lambda is equal to one number already because we chop it very small, and we multiplied both together, which we will get like this area of the square, because since this is delta x and this is lambda, you understand that this is the same thing. You do this manually and you do this by graph by multiply the number of lambda with the delta x, and you keep doing this with other section and other section and other section and other section. Boom, you got what? You got the area under the curve, which is the definition of integrating. Yeah, so you do this integration for finding the whole mass. You gotta integrate like the lambda function and the dx, because this is delta x. So if it's in calculus, you just chop them really small, so the delta sign turn into the d sign. And yeah, this is how you got the whole mass, which is like this section of the equation. Yeah, so if you don't paying attention, I will tell you again. We got the density function, which is lambda, and we want to find the mass of each section so that we can use in a lot of stuff. We do the lambda multiplied by L, but the lambda is not constant throughout the rod, so you must chop it in the small section, so you can get like the mass of each section. So the mass of this section is equal to this multiplied by this. And if you want the mass of all of the section, you just do this again and again and again and again. It suddenly turned out to be the integration of this to get like the mass of the whole rod. So if you don't want to remember all this stuff, I have like one of the easy techniques for you, which is you can do things like lambda is equal to the mass between divided by the length. You can just say that, oh, this is calculus, now we gotta throw it very small, and then you can just multiply both sides by dl, and you got the lambda dl equal to dm like this. And if you want to, and this is the formula that you need to use for finding the mass of one specific length. This is really important. This is very important question. I want you to take a closer look with this. The dl here is mean that the specific length of this rod, like this place, you might call that dl, has a mass of dm. What is d even called in this context? D is called very small, so the m here stand for this whole mass of the rod, but the dm here means the very small mass that is here in this specific section called dl, which dm is equal to lambda dl. So you can find the dm here by using this lambda dl section, and you get the mass of this specific section, which you can use it for other uses, especially this one, because in this part you need to multiply the each masses in each section by the displacement in each section, so this will come in handy later, but yeah, we'll just talk about that later. We'll do this first. So yeah, dm is equal to lambda dl, and if you want to get the mass of this whole rod, what you need to do is integrate, because integrate is like another word for roaming อะไรวะ collection of the every section between 2 points like this. You do this นะ แล้ว you ก็ integrate จาก 0 ไป เดี๋ยวกูต้องพูดอังกฤษหรือเปล่า yeah, you integrate from the mass equal to 0 to the mass equal to m, which is like the whole rod. You have like the mass m, because you want to know what this is. You don't know any of this, alright, but you know this part, and you want to integrate the L, which is just another fancy term for x. You can just use this x because we're gonna integrate from x equal to 0, which is like the start of the rod is in the x equal 0 here, to the x equal to L, because the end of the rod is in the point where x equal to L. So you do this, and if you do this, you get like the mass of the whole rod, because in this part you get like integrate dm, it's just cancel each other out, so you got like this m minus 0, which is just m, equal to which this m is stand for the mass of this whole rod. And another side, you got this integrate lambda dx part. What is lambda? You have the equation for it, right? It's 1 plus this thing, so you write that down. Yeah, and then you just integrate it like the normal sane person. So if you already know integrate, this will be really easy for you, but if you don't, you must learn some calculus here. So this you got x, and this you got x power third and right 3l square, and you need to substitute this with 0 and l, which you got just like this, which is equal to l plus l third like this, and you got like a 4 of third l. Yeah, this is the mass of this whole things, and if you wonder, this is in kilogram already. But I want you to see this. You see this section, which I write L plus L by 3. This is the indication that what you did might be right, because at least you got the same unit in addition like this. Like you got this L and you got this L right here. Because if you write this and you got like something like L plus L2, you must be concerning to some extent, because you know you can't add the two things with different units. So yeah, you might be right, you might be wrong. It's depending on what you did up here and what the unit has been, you know, going. But I'm so lazy, so I didn't write any of the units here, but at the end, yeah, so whatever, I got like the mass of this whole rod is equal to 4 third L. Yeah, you got this? Yeah, I'm sure you got this, you are smart. And is this the same? Yeah, this is the same with what I got in the class, which is nice. Okay, now we gotta find this section now, and it's that in that section what you need to do is multiply the little m with the x value that that little piece is, how far that little piece is from the center, or 0 0 with you know that thing. So if you want to know how far this little section is from the 0 0, what you need to do is yeah, you need to find out how far is that. And in this case it's just an x value, isn't it? Because you already defined x like this, and x is start from 0 0 here. And if you want to know how far this little section is this length is just an x. So what you need to do is you remember that I told you before this little section has a mass of dm, and yeah, it's far from the 0 point equal to x. So if you want to find this section, you can just tell that this section have like this quantity of x and dm, and this is the quantity of just this specific part right here. And it's the same stuff. If you want the next little part of it, like this part right here, you must do the same thing over and over again until you got like all of the stuff right here in this formula. So it will be just, you know, integrated. It's the same mechanic that I told you before about this graph. But now it's not the lambda anymore. This time is like the mass of that little specific places, you know. And this have some masses and this have some x's, you know. And if you want to know what does this value will be, you must multiply both of them together, which like the x here, which is the large number that span from like, you know, 0 to that specific place, with the little mass that in each place, which you just, you know, chop it up into little place like this. And then you keep doing that until you get the whole graph, which is just another word for integrate this thing from 0 to like what, m, because you want the whole mass. And this thing will be this thing. This 2 is equivalent, but this is you use when you have like a simple things like this. But when it's become the function, you need to use this formula, which is important, you know. Or if you understand the whole process and you want to remember something into like the exam room, you can just, you know, remember this formula and think that this section here is just m and x multiplied with each other, and you sum it up into like the long axis. So you got like this integrate x dm. Yeah, you can remember this. And you might wonder why is it not integrate m dx, because you know that's not how it works. If you do it that case, you get like the masses, like you get, let me find a new color, you get like the mass of this whole piece multiplied by just the length of this little section, which is not what you want. So you want to use the integrate x dm, not the m dx. Okay, yeah, so now we gotta do the maths now. You want to integrate x dm from 0 to m, but you don't know how relation of this x and this m is, so you gotta specific a little bit more, which we know like this part that dm is equal to lambda dl, right? You remember from this little easy equation, you turn it into calculus and you got this. Yeah, and then you use substitution like this. dm, no, we don't want dm, we want lambda dl, so we just do that. And now that the d has changed from m to l, we must change this boundary condition to it start from 0 to the m, which indicate it's like the whole mass. Now we gotta change to 0 to the l, which indicate like the whole length of this object, you know. And yeah, we know the lambda here because, you know, the problem has given us this, so we gotta substitute that also. Lambda is equal to 1 by this stuff. And we're not gonna write the L anymore because this is confusing, because, you know, this section is L and you might confuse which L do I use. So we gotta write this in the X form because, you know, it's actually my bad that I used the L here. I should not have used L since the first place, because, you know, it will cause a confusion, because this problem has a constant of an L and the variable of an X. You always want to use an X, Y, Z and coordinates, you know, because you might get confused like I do. And if you confused why didn't I use L now, it's just because I use L in the first place to, get you guys familiar with this formula, which is like L stand for length in high school. But in this context, L is mean the length of this whole rod, not the length to this section that we want. If you want the length from this specific section that you want, you must use an X because that value was indicated by an X. So yeah, we gotta use the X instead. And you multiply this up together. If you want to do the stupid by part stuff, you got like this X plus X3 by L2, something like that. And you integrate all this stuff, which you got like this thing plus this thing and this thing. And then you gotta do this, and then you get just L squared plus 2 plus blah 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 blue blue blue. Then you got like this cancel out, L square by 2 and by 4, and you multiply this by 2, and you got 3/4 of the L square. Yeah, and this thing is like this value like here, so you can calculate XCM now from this two value that you got. So yeah, if you want to write this formula in the somewhat calculate way, you can use this XCM is equal to integrate XDM that I told you before divided by the whole mass, or you can do that by integrate lambda dx, but it's just the whole mass. I want to write this because it's easier to understand, and you can just change this into whatever formula you need to find the whole mass, because sometimes it's not that, because like I told you, there are multiple ways you can find the density, so it's not necessary be the x like that. But yeah, this is like the whole fundamental of it. Then you just take this 2 and plug it in this equation, and then you got like 3/4 L squared divided by 1/4 L, and then you put this back up, and then you get this, and this L cancel out, and you got like 9 by 16 L, which is the same as I did here. Yeah, but it's much slower because I need to explain everything, and I hope you understand this by now, because if you understand, it's nice, because you'll find like a shit ton lot of questions like this upcoming in the future lessons and problem, because this is like the basic of like the whole physics with calculus stuff. You need to know like what you want to find and how to find it exactly in the calculus way, and then you do some maths, and then you got the answer that you want. So yeah, see you again later. When you have any question, you can feel free to ask me. This is my Instagram. You can ask me if you're afraid to talk to the teacher, but yeah, you can talk to the teacher because he will definitely know more than I do, because I'm just a fellow student, and sometimes I get lazy and don't answer people's questions and stuff like that. So yeah, hope you enjoy and understand this video. See you again if needed. Bye bye.